So this is joint work with PhD student Jatin and our advisor Umut at Carnegie Mellon. This work is guided by, more generally, by a question of whether or not parallel functional programming can be fast and scalable. This has been a long-standing question in the community because functional programming has great promise for parallel programming, except for the question of efficiency. Or for a long-standing time, the question of efficiency has been a difficult one, okay? And the main challenge is really one of memory management, not so much of compilation, say, but actually in the runtime system, how do you implement an efficient garbage collector for a parallel functional language, okay? Functional programs are somewhat unique in that they have a high rate of allocation. Rather than modifying something in place, functional programs tend to allocate something fresh, okay? So this creates a high rate of allocation, and therefore there's a very heavy reliance on garbage collection to get good space efficiency, okay? Now in the parallel setting, the rate of allocation grows linearly with the number of processors that you're using, or it can grow linearly with the number of processors, okay? So we have a much more difficult garbage collection problem, essentially. This garbage collection for functional languages is fundamentally harder than garbage collection for imperative languages in some sense, okay? Now, we, over the past 5 or 6 years, have been working on this problem, and we can definitively say at this point that actually, yes, parallel functional programming can be fast and scalable, okay? And the way that we've shown this is through a property that we call disentanglement. So at 10,000 feet, just a quick high-level sketch of what is disentanglement. I'll give you an informal definition here, and then we'll talk more formally later, but the idea is that concurrent tasks remain oblivious to each other's allocations. So if 2 tasks are executing simultaneously, concurrently really, and they are both performing allocations, then disentanglement says there should not be pointers across the gap. They shouldn't point across to each other, okay? So this turns out to be very closely related to determinism. In particular, we show that programs that are determinacy race-free, that's a very strong correctness condition that guarantees determinism. If you have that property, then you get disentanglement for free. And so this means that it's basically, it emerges naturally in functional programs, okay? And what's really cool about this is that it enables efficient and scalable automatic memory management, okay? And the intuition here is no cross pointers. And cross pointers are a long-standing kind of challenge in designing an efficient parallel garbage collector, that pointers across separately, concurrently generated regions of memory can really like degrade the scalability of your collector. So based on this disentanglement property over the past 5 or 6 years, we've been developing this compiler that we call Maple. It's based on Milton, and we support the full standard ML language. And what we've done is we've extended it with a single construct that we call par. And par basically just evaluates 2 things in parallel and returns their results back to you, okay? This is a fairly robust implementation. You can go and use it right now. In fact, it's being used at Carnegie Mellon. Over 500 students approximately every year use it. We use it as part of our undergraduate program to help teach parallel algorithms, okay? And so we have a completely new runtime system. It's basically the compiler is Milton, but the runtime system is a new runtime system based on disentanglement. And one of the key features actually is that we have a provably efficient algorithm that we presented at Popple in 2021. Based on disentanglement, okay? Now we're getting really, really good performance with this. In comparison to a few other memory managed languages, for example, on comparison to Java on 72 cores, so this is a decent sized multi-core machine, we're about 3x faster on average across a variety of benchmarks that we've considered. And these are benchmarks that we've ported from state-of-the-art C and C++ benchmark suites. So in comparison to Java, what we're seeing is on average about 3x faster and about 4x less space. In comparison to Go, about 2x faster and maybe 30% less space. And now we've actually just recently been doing some comparisons with the new multi-core Camel project, and I'm really excited to see so much interest in parallel functional programming in this community. Now, multi-core Camel is quite a bit different from our compiler. Like, for example, our compiler is a whole program compiler. That's one source of improved efficiency. But also by taking advantage of this disentanglement property, we're able to get significant speedups in comparison to a Camel. And just going a bit further, I'd like to say that we're getting really fantastic performance in comparison to C and C++. The margins there are approximately a factor 2 in terms of time on average, but the space footprint actually is about identical on average in the benchmarks that were considered. Okay? So all of this sounds really great. What's the problem? And what's the focus of this talk? Okay. So the issue is that not all programs are disentangled, of course. This is a restriction. You have a restriction where you can't communicate across the gap, okay? And if we had a GC that assumed disentanglement, but didn't try to check for it, then very bad things can happen, okay? And just a quick example, here we have two tasks running in parallel, and these little white boxes are the memory that those tasks are allocating, okay? And there's some pointers between these objects that they've allocated. Well, now, if a garbage collection happens on the left-hand side, one of the things that the garbage collector may want to do is compact memory. And in order to compact memory, you need to move objects around. You need to rename them, essentially, give them a new location. Now, when you do this, you need to update all references to any relocated object, but a garbage collector based on disentanglement essentially assumes that cross-pointers are impossible and doesn't try to even check for them, okay? So this will cause a dangling pointer, very, very bad, terrible things could happen. And so we need to enforce disentanglement. And that's really what we focus on in this particular paper, the question of how to enforce disentanglement. Okay. So the immediate question you might have is maybe we can do it statically. Okay, and this turns out to be really tricky, and we've worked on this problem for quite some time and haven't yet gotten something that we feel is quite ready. Okay, so there's a few things to consider here. How might you go about doing this? Well, the first thing you could try is disallowing in-place updates, okay? This works. This guarantees disentanglement by construction, but it's extremely inefficient. And in particular, this is really important for parallel computing. Perhaps the most fundamental operation in parallel computing is a parallel fill array. You allocate an array, and then in parallel, you fill in each element. That fundamentally is mutation, regardless of whether or not at the surface level it appears to be mutation, okay? At the low level, the garbage collector sees mutation. It is fundamentally mutation, and we need to be able to support it efficiently. Okay? So you might think there may be some sort of type and effect system would be able to enforce disentanglement. And we've tried to develop something like this, but basically the problem that we run into is that it's too conservative. We have a big benchmark suite of approximately 30 fairly sophisticated parallel algorithms that we've ported from C and C++. Okay? And a very, very common thing is that parallel algorithms, despite wanting to be deterministic, that's a common correctness condition, often will utilize a very small amount of non-determinism to gain significant performance advantage. Okay? And the intuition here is that with a little bit of, say, atomic in-place modification, maybe a compare and swap, that kind of is on the fly communicating with a concurrent task, you can eliminate a large amount of unnecessary synchronization. Okay? And this becomes very challenging to design something that essentially is both non-deterministic and could have aliasing between different objects that have been allocated. It seems very difficult to detect this property statically, but it is something that we're still working on and we're interested in pursuing. So what we do in this paper is we instead do it dynamically. Okay? And the intuition is that we want to monitor individual reads and writes to memory. And if we ever detect entanglement, then we can terminate the program safely with an error message. You could generalize this to, say, a dynamic exception that could even be handled if you'd like, but our implementation at the moment is fairly simple. We just terminate. Okay? So this is very similar to the concept of race detection, if you've seen race detection in other contexts. Now, the difference here is that we're able to show that entanglement detection can be accomplished with essentially zero overhead in practice. Race detection, as many of you I'm sure are familiar, has massive overheads. A typical sort of overhead that you see is a factor 10 on a single core. And those overheads tends to actually increase as you go parallel. Our entanglement detection results in this paper are fully parallel, and the overheads are consistent across different core counts. And what we're seeing is that it's on average about 1% across the board. That's for both time and space. And actually the max we've seen is about only 10% overhead. Okay. One of the key contributions in this paper is trying to identify whether or not the entanglement detection algorithm is good. Okay? What does it mean for the detection algorithm to be a good algorithm? So we formulate two conditions here. We call soundness and completeness. Okay, two sides of the coin. The non-negotiable one is that it needs to be safe for disentanglement. Okay, so it should be safe to run a disentangled program. It should be memory safe to run a disentangled program. Okay, and that can be formulated essentially as a soundness property for disentanglement, or another way of saying that is there's no alarm that you miss. Okay. Now on the other side of the coin, we have completeness. And in some sense, this is just as important, because what we found is that any sort of static technique that we were looking at was too conservative. It would rule out too many programs. Okay? It would rule out half of our benchmark suite. Right? So this particular technique is able to allow for all disentangled programs to run to completion. Okay? Now I should say that this is relative to a particular execution because we're dealing with non-determinism here. Okay, but I'd be happy to talk about that later. It's a bit of a subtle point. Some details of this algorithm for you. So how do we actually more formally define disentanglement and work with it in this context? Well, one way of discussing entanglement and disentanglement is in terms of a computation graph. So a computation graph is, think of it as a history of execution or a trace of an execution, okay? Where you are writing down what the execution did, but you're abstracting away details of scheduling, okay? So the vertices here are individual instructions and the edges are sequential dependencies between those instructions, okay? And in some sense, the width of this computation graph is the parallelism that you're getting at any moment, okay? And that parallelism grows and shrinks as you run your program, okay? Now, in the computation graph, we can annotate different instructions. We can keep track of where allocations occur, and we can keep track of where those allocations are used. And when I say use, I mean even like holding a pointer to a location, we consider a use, because that's what's relevant for garbage collection. Okay? But this also includes accessing a location, updating a location. Okay, that all constitutes a use of a location. So it turns out that you can define disentanglement as a path property. That basically your uses between allocations, every allocation precedes all of the uses of that allocation. Okay, so basically just that your uses of your allocations respect the sequential dependencies that are inherent to your program And entanglement is when you essentially get a use across. So the algorithm that we implement in this paper and that we analyze in this paper is extremely simple. It's exactly the definition, essentially. We build the computation graph during execution, okay? We annotate all of our allocations with a vertex in the computation graph. And then the key result is that we only need to check the results of memory reads. So anytime that you're loading something from memory, you get back the name of a location, you have to check, is it allocated before me? And that's a dynamic check. And if you detect that it's not allocated before you, well, then you've detected entanglement, and that's when we throw an alarm. Okay. Now, you might be wondering, how is it possible that you could implement this efficiently? Like, we're building this computation graph, okay? Well, first observation is we can coarsen the computation graph. You don't need individual instructions, but actually you only need things at the granularity of whole tasks, okay? And in a parallel program that has good granularity control, which is a necessity for good performance in the program anyway, these tasks are actually large enough that essentially the overhead of maintaining the computation graph goes down close to zero. Okay? And in particular, what we're using here is a technique called SP order maintenance, which is a technique that we got from the race detection literature. A lot of this work is inspired by that literature. Okay? And SP order maintenance is essentially a very clever encoding of the computation graph that, to be honest, uses essentially no additional space at runtime. Now, the way we actually implement this is with a read barrier. So every time that you dereference something in memory, you have to do a check. Now, that's like only mutable dereferences. So what this means is that there's already no overhead for immutable data. Okay? And one of the key contributions in this work is proving that immutable data is always safe for disentanglement. Okay? Now, one of the cool things that I don't have time to talk about in the talk, but I hope you see in the paper, is that we have a really effective fast path for the read barrier. That essentially, in our experiments, we see that the fast path of the read barrier, which has very, very low overhead, is being hit essentially like 99.99% of the time. And that's like the key to why this performs so efficiently. And we call that idea entanglement candidates. It's a way of tracking potentially hazardous, mutable objects at runtime. Okay? And I'll just mention it's very closely integrated with memory management in order to make this safe for garbage collection. Okay. So all of this is available in Maple. You can go play with Maple. And I should mention the performance results that I mentioned earlier, 3x faster than Java, 2x faster than Go, that includes the cost of entanglement detection. Okay, so it's a fair comparison in the sense of like our language is memory safe and we're comparing against other memory safe languages. Right. So what we show in this paper really is that this disentanglement property, which seems to be extremely important for efficient parallel memory management, is efficiently checkable at runtime, okay? And we have a Maple implementation of it, which is practical and fast. And I really encourage you all to go check it out. And one avenue for future work that we're really excited about that this opens up is the possibility of what we call entanglement management. And the intuition there is that at the moment of detection, we could handle entanglement dynamically, fix it up. That might cost a little bit, but we can fix it up in that moment, and therefore essentially make this disentanglement property become strictly a performance property. Right now, it's kind of halfway between performance and correctness, and we'd like to turn it into a property which is purely a performance property. And I believe that this entanglement management idea can get us there. If you would like to hear more about disentanglement, please come see my keynote at the ML workshop on Thursday, and I'll be going into the details of how the garbage collector works and all of that. But thank you so much for listening, and thank you. Yeah,
thank you,
coming.
Sam.